Albert Einstein, one of the greatest geniuses in physics, revolutionized our understanding of the universe with his theory of relativity. Published in two parts, special relativity in 1905 and general relativity in 1915, this theory introduced concepts that transformed how we view time, space, and gravity. Before Einstein, physics followed the principles established by Isaac Newton, which, although accurate in many situations, could not explain certain phenomena observed in the universe. Since its formulation, the theory of relativity has not only transformed physics, but has also left a deep mark on popular culture. The idea that time can dilate and space can contract challenges our common sense and sparks the imagination of writers, filmmakers, and science enthusiasts. Movies, books, and TV series often explore concepts of time travel and parallel universes, inspired by Einstein's theories. This cultural influence demonstrates the profound impact that science can have beyond labs and universities. The theory of relativity has become a symbol of the power of the human mind to explore and understand the mysteries of the universe, stimulating curiosity and creativity worldwide. In modern physics, time is often described as the fourth dimension, essential for describing events in the universe. Unlike the three spatial dimensions, time is a dimension in which all events occur in sequence. The theory of relativity introduced the idea that time is relative and can vary depending on speed and gravity. This understanding of time as a flexible and variable dimension revolutionized science. Instead of being a universal constant, time can expand or contract depending on the surrounding conditions. This flexibility is crucial for exploring the possibility of time travel, offering new perspectives on the nature of our universe. Einstein's relativity suggests that time can expand or contract, a fundamental concept for the theory of time travel. When an object moves at extreme speeds or is in an intense gravitational field, time for that object passes differently compared to an observer at rest. This phenomenon is known as time dilation. Time dilation has been confirmed by numerous experiments, including the observation of subatomic particles and atomic clocks on airplanes. These studies demonstrate that time indeed slows down for objects moving fast or in strong gravitational fields, providing a solid scientific basis for the idea that time travel could be more than just science fiction. Einstein's special relativity establishes that the speed of light in a vacuum is a universal constant and the maximum speed limit in the universe. This has profound implications for our understanding of time. As an object approaches the speed of light, time for that object passes more slowly compared to an observer at rest. This phenomenon, known as time dilation, is one of the most fascinating predictions of special relativity. Time dilation implies that if we could travel at speeds close to light, we would experience time very differently from those who remain on Earth. This concept is fundamental for exploring time travel, suggesting that time can be manipulated by changing an object's speed. Einstein's theory provides a solid scientific basis for discussing time travel. Time dilation and space contraction are concepts that indicate that time is not absolute and can be altered under certain conditions. Although challenging, these ideas open the door to the theoretical possibility of traveling through time. The idea that we can travel through time is more than a science fiction fantasy. It is a direct consequence of the laws of physics as we understand them today. Although we are far from achieving time travel, Einstein's theory provides us with the conceptual tools to explore this possibility. Several experiments have proven the time dilation predicted by special relativity. One of the most famous involves synchronized atomic clocks placed on airplanes. After the flights, the clocks on the airplanes, which moved at high speeds, showed a slightly slower time compared to the clocks on the ground. This experiment, known as the Haffel-Keating experiment, was an empirical confirmation of Einstein's predictions. Moreover, subatomic particles known as muons, which move at speeds close to that of light, also demonstrate time dilation. Muons generated in the upper atmosphere reach the Earth's surface in greater numbers than expected due to the slowing of time they experience during their rapid descent. These results provide strong experimental evidence for the theory of time dilation. Special relativity also predicts space contraction, which occurs when an object moves at extreme speeds. This spatial contraction means that distances traveled by a fast-moving object appear shorter than those measured by an observer at rest. This phenomenon is known as Lorentz contraction and has significant implications for the idea of time travel. If a traveler could move at speeds close to light, they would not only experience time dilation, but also travel much greater distances in less time, from the perspective of an outside observer. This combination of space contraction and time dilation offers a tantalizing view of how rapid interstellar travel could be possible, at least in theory. The twin paradox is a thought experiment that illustrates the implications of time dilation. Imagine two identical twins. One travels through space in a ship moving at speeds close to light, while the other remains on Earth. According to special relativity, the traveling twin will experience time more slowly relative to the twin who stayed home. Upon returning, the traveling twin would be significantly younger than the twin who remained on Earth. This paradox is not just a theoretical curiosity, but a practical demonstration of how time dilation affects the passage of time. It challenges our intuitive notions of linear and simultaneous time, providing a deeper understanding of the realities described by Einstein's theory. Black holes, predicted by Einstein's general theory of relativity, are regions of space where gravity is so intense that not even light can escape. These extreme cosmic objects challenge our understanding of the universe and open doors to fascinating speculations about time travel. Theoretically, black holes could distort spacetime in such a way that they create shortcuts known as wormholes. Wormholes, or Einstein-Rosen bridges, are hypothetical passages that could connect different points in spacetime. If these structures exist and could be stabilized with exotic energy, they could allow instant travel between distant locations or even different times. Although still highly theoretical, wormholes continue to inspire research and debate about their possibilities. The idea of traveling faster than light, FTL, is a recurring theme in science fiction, but faces significant challenges in real science. According to Einstein's special relativity, the speed of light is the maximum limit for any object with mass. Reaching or surpassing this speed would require an infinite amount of energy, making FTL travel currently impossible. However, theoretical concepts like the warp drive, which distorts space around a ship, continue to inspire scientists and enthusiasts. Although these concepts remain speculative, ongoing research in particle physics and relativity may one day reveal new methods to circumvent the limitations imposed by the speed of light, turning the dream of interstellar travel into reality. Einstein's theories have not only reshaped physics, but also had a profound impact on popular culture. Concepts such as time travel, time dilation, and wormholes have become common elements in science fiction stories. Movies, TV series, and books frequently explore these themes, using Einstein's ideas to create intriguing and exciting narratives. This influence demonstrates the power of scientific theories, not only to explain the world but also to inspire human imagination. The way popular culture adopts and expands Einstein's ideas shows the deep connection between science and creativity, stimulating generations to ponder the possibilities of the universe. The idea of building a time machine has fascinated scientists and writers for decades. According to the theory of relativity, it is theoretically possible to construct a time machine using extreme structures of space-time, such as wormholes stabilized with exotic energy. However, the practical realization of such a device faces numerous scientific and technological challenges. Beyond technical difficulties, there are fundamental questions of causality and paradoxes that need to be resolved. Even if we one day manage to build a time machine, it will be crucial to develop a deep understanding of the implications of altering past events and how it would affect the present and future. Until then, the idea of time machines remains a mix of scientific theory and creative speculation. The grandfather paradox is one of the most famous paradoxes related to time travel. It suggests that a time traveler could theoretically go back in time and prevent the existence of their own ancestors, creating an unsolvable loop. This paradox challenges our notions of cause and effect and raises profound questions about the nature of causality. Physicists and philosophers continue to debate these paradoxes, exploring theoretical models that could allow time travel without logical contradictions. One proposal is the multiple universes hypothesis, where each decision creates a new temporal branch, thus avoiding paradoxes. These discussions are essential for understanding the limitations and possibilities of time travel. Traveling to the past is one of the most intriguing and controversial aspects of time travel. While the theory of relativity allows certain types of travel to the future, traveling to the past presents additional challenges, especially related to violating fundamental laws of physics, such as causality. Various theories have been proposed to circumvent these barriers, including the use of wormholes and other exotic solutions of spacetime. Each of these solutions comes with its own complexities and ethical implications, raising questions about what could happen if we could alter historical events. Beyond temporal paradoxes, there are considerations about the stability of the universe and the preservation of the timeline. These discussions remain at the forefront of theoretical physics and philosophy of science. Unlike traveling to the past, traveling to the future is scientifically plausible and has already been demonstrated on a small scale through the time dilation observed in astronauts who spent time on orbiting space stations at high speeds. This phenomenon, predicted by Einstein's relativity, suggests that, in theory, if we could travel at speeds close to light, we could advance in time more rapidly than those who remain on Earth. This possibility opens a range of practical and theoretical questions about how we could use this capability in the future, whether for long-duration space travel or even to skip time periods within our own planet. The ability to travel to the future may have significant implications for space exploration and the future of humanity. Albert Einstein's legacy is vast and permeates many aspects of modern science. His theory of relativity not only transformed physics, but also established the foundation on which contemporary research on the cosmos and quantum mechanics is built. The quest for a unified theory that can reconcile general relativity with quantum mechanics remains one of the greatest challenges of current physics. This ongoing effort to expand and refine Einstein's theories demonstrates the dynamic nature of science, where each generation of scientists builds upon the foundations of those who came before, always striving to understand more deeply the mysteries of the universe. Einstein's contributions continue to inspire new discoveries and advances in various areas of physics. The idea of time travel has a profound cultural impact, influencing everything from literature and cinema to how we think about our own lives and the flow of time. Stories that explore time travel often address themes of regret, change, and the possibility of a new beginning, reflecting our own concerns with the past and the future. Moreover, Time travel serves as a powerful metaphor for the human desire to explore the unknown and to shape our own destiny, illustrating our eternal quest for knowledge and understanding in a constantly changing world. The way these ideas are portrayed in popular culture continues to evolve, inspiring new generations to dream about the possibilities of what could be. Einstein's general theory of relativity expanded our understanding of the universe by demonstrating that mass and energy can curve spacetime, a revolutionary idea that fundamentally altered how we understand gravity. This curvature of spacetime is what we perceive as gravitational force, and it is a central concept for explaining astronomical phenomena, from the movement of planets to the behavior of black holes and gravitational waves. This understanding also suggests that if we could manipulate these curvatures, we might be able to create shortcuts in spacetime, known as wormholes. Although the practical viability of such structures is still highly speculative, the idea offers a fascinating field of study that challenges the limits of current technology and stimulates scientific imagination about what could be possible. Singularities are points where the known laws of physics collapse, commonly associated with the centers of black holes. According to general relativity, these regions of infinite density and extreme curvature of spacetime could create unique conditions for time travel. Isolated singularities, or those in wormholes, could, theoretically, serve as portals to other eras or universes. The existence of spacetime singularities opens a vast range of possibilities for time travel and space exploration. However, the exact nature and implications of such phenomena remain a mystery. Investigating these extreme phenomena tests the limits of our scientific understanding and offers a unique window into the strangest aspects of the universe. Strong gravitational fields have a measurable effect on time, a direct consequence of general relativity. The stronger the gravitational field, the more slowly time passes, a phenomenon observed in experiments with precise atomic clocks placed at different altitudes. This effect, known as gravitational time dilation, has important implications for satellite navigation technology and theoretical physics. This principle suggests that if we could manipulate gravitational fields in a controlled manner, we could theoretically alter the flow of time. Although we are still far from having the technology necessary for such large-scale manipulation, understanding these effects allows us to dream about future applications, such as traveling through space-time by adjusting the gravity around a ship. To carry out time travel or stabilize wormholes, the theory suggests the need for exotic energy, a form of energy with negative pressure properties, which defies many of our current understandings of physics. This exotic energy could, in theory, counteract the natural tendency of space-time to close wormholes and allow the creation of stable portals for time travel. The search for practical ways to obtain and use exotic energy is one of the most intriguing challenges for physicists today. Although we are still far from a practical application, ongoing study of this energy opens new avenues for exploring the universe in ways that previously belonged only to the realm of science fiction. Particle physics offers some of the most intriguing possibilities for understanding time travel. Experiments with subatomic particles, such as those conducted in particle accelerators, demonstrate behaviors that defy our conventional understanding of time and space. For example, some particles appear to interact in a way that implies a reversal of time, where effects precede their causes under specific conditions. We bring you an incredible series of videos like this one. Subscribe to our channel so you don't miss out. These phenomena, although confined to microscopic scales, suggest that the laws of the universe may allow exceptions to the general rules of causality and temporality that govern our everyday experience. Studying these particles not only expands our understanding of the universe, but may eventually pave the way for manipulating time on larger scales. String theory is one of the candidates for a theory of everything, seeking to unify all the fundamental forces of nature into a single theoretical framework. Within this context, the theory also offers fascinating perspectives on time travel, suggesting that the universe may contain additional dimensions that could, theoretically, allow types of time travel or interdimensional travel that are inconceivable with our current understanding of physics. Although still highly theoretical and lacking experimental proof, string theory continues to be a promising area of research. Its development could eventually lead to new technologies capable of exploring these extra dimensions, potentially transforming concepts of time travel from science fiction into scientific reality.